let's get started with the second part here, which is explaining classifiers. Think of this as yet another mode of reasoning about classifiers. It's something that has been receiving attention recently with the proliferation of AI systems. People want to know why they do what they do. And as I said, this is very current work with Andy, who's actually with us, and Arthur. And we will be building on what we did in part one. But let me first make a key distinction, because the word explanation now is being discussed a lot, and there's different modes of explanations and different things that people have in mind. There is the notion of explaining a decision, where you would come and say, why did you predict that Sue will have a heart attack? Why did you recommend admitting John to the PhD program? And so on. Here I have a classifier, and then I have an instance, and then the classifier made a decision on this instance. And then I'll say, why did you do that? This is opposed to what? This is opposed to explaining a system or process. For example, why do people have heart attacks? That's very different than, why did you predict that Sue will have a heart attack? What does it take for a student to be admitted to the PhD program, and so on? In the second case, I'm explaining a system or a process. And in the first case, the input to the analysis or to the explanation generation process is a classifier and an instance on which you made this decision. And that's what we're going to be talking about next. For the second type, where you're trying to explain a system or a process, you need, in a way, something more demanding. You need a model of the system process, or what people would call a model of reality. There has been a long tradition, not just in AI and philosophy, in thinking about explanations. But they were more of the second type. Today's demands and this notion of accountability had put some new criteria or constraints on what is an explanation. So there's been a lot of thinking recently about the different modes and types of explanations and what may be needed, for example, from a legal point of view versus from an understanding point of view. In the second type, I comment on this briefly in the next version of my position paper, which is not yet online, but it will appear in the CACM. Okay, so here's the deal. The idea is I want to try to do the explanations on the symbolic form. We've seen in the previous part that you may have a classifier that's probabilistic, or even more specifically, let's say a naive-based classifier, but that classifier is a symbolic decision function in a sense, and I want to have that symbolic decision function in tractable form, and if I do, I want to do the classification on it, or the explanation on it, and that's what we're going to do. So the premise here is that the symbolic decision function facilitates the computation of explanations, assuming that it is tractable as well. Okay, so we look at two types of explanations. The first type is called an MC explanation. MC stands for minimum cardinality. You're going to see that later, where the name comes from. But the idea is this. You have a classifier, and it did classify an instance as yes, right? And let's assume in this case, for simplicity, that features are either positive or negative. And even more so, that positive features push towards a yes decision, and negative features push towards a negative decision. So here you have a classifier that classifies an instance as yes, and I'm asking it which of the positive features are responsible. So let's say you have 20 features. 9 of them, the current instance has 9 of them as positive and 11 as negative. And then the classifier said this instance is a yes, it's a positive instance. I'm asking you which among the 9 are really responsible. And what I want you to do is find me the smallest subset of these 9. That maybe 3 of them, if they were positive, even if all of the others were negative, you would still classify as positive. Does that make sense? So in a way, even though you have 9 positive features, only 3 of them are really what matters. The others can all be negative and you still make the same decision. So you're pinpointing the reason why you classified something positively, and similarly for this guy. So this is one type of explanations. We'll see concrete examples in just a little bit and how easily you can compute these guys. Now there is another type of explanation. The other type may be a little bit more robust. What it says is this, and it's called PI explanation. You'll see where PI comes from later. You have 20 features, some positive, some negative. I want you to identify a smallest subset of these features, smallest. Let's say 4. And these 4 could be either positive or negative, doesn't matter. So that if you keep these 4, you can do whatever you want with the others, and the decision doesn't change. So these 4, let's say positive, negative, negative, positive, right? As long as you fix them, vary the others as you wish, and your current decision will not change. We will call this a PI explanation. And we'll see examples of both in just a little bit. And in fact, we'll use this as a running example. This happens to be a naive-based classifier also that is meant to decide whether to admit an applicant to an academic program. So this is the class variable admit or not. And it's based on whether the applicant had work experience, whether they're a first-time applicant, whether they passed the entrance exam, and whether they have a suitable GPA. So all of these are positive, negative. And these are the CPTs for the features, and this is the prior. We're good? Okay. So the idea is I want to do explanations on this guy, and as you know, here's the instances. There are 16 of them because we have 4 features. And if you compute the posterior on the class variable, you get these. I think we use the threshold of half. These are the decisions, so we know that really that's our decision function, correct? And to do explanations, I want to get that decision function in some tractable form and then use it for that basis. And in fact, we did do that. But to illustrate the notion of PI explanations and MC explanations, we don't even need the OBDD. We need the OBDD to compute them, but to say what they are and give you examples, we can operate at this level, and that's what we're going to do next. So here's some examples of minimum cardinality explanations or MC explanations. So remember, features, decision. So this is our decision function, symbolic decision function. And what we did here is enumerated for every instance the corresponding explanations. So consider the following student. This is an applicant. Got positive on every of the 4 things that are considered. It's this guy. So what was he classified? Positively, admitted. And then you ask, why was he admitted? And in this particular case, the MC explanation is this. What does that say? Even though you got everything positive, it was the first and the last are sufficient. Work experience, W, and the good GPA would have admitted you anyways. You did not need to be a first-time applicant or even pass the first-time exam. Right? So what happened here is, out of the 4, we identified the smallest, and these were 2. So in this case, it was unique. Let's look at, sometimes it's not unique. These are all negative. Okay, let's look at another example. Here's another student. They got work experience, but didn't do well on the other 3. All 3 were negative. They were not a first-time applicant, so they're applying again, did not pass the entrance exam, did not have a good GPA. And this particular student was not admitted, so the decision was negative. And the question why, or what were the reasons for that? Now, remember in this case, it is these 3 that basically pushed the negative decision. And what this says is you really don't need 3. If the last 2 were negative, you would have not been admitted anyways. And the second explanation says F and G being negative would have done it as well. So it looks like in this case, G was there, and then either E or F would have done it. You didn't need both of them. You guys see what's going on? So think about it. You have been admitted because of these things. That's the instance. You would still be admitted if you only had these, not all of them. And it identifies a smaller subset. And the other time you were not admitted because of these negative things, but you will still not be admitted even if you had fewer negative things. And that's basically the minimum cardinality explanation. And sometimes there are multiple of them, as you can see. So what happened in this case is we just tabulated for every instance, what are the explanations. You look at this negative instance here. In this case happens to be 3 of them. So you have 3 negative features, negative decision, but there are 3 combinations, each involving 2 negative features that would still lead to negative decision. Okay, let's look at the prime implicant explanation. So in this case, here's a student, and this was admitted, right? So, and the question is, out of these 4 features, is there a smaller subset that if you fix, you can do whatever you want with the other ones? Another way, a smaller subset of features that make the remaining ones irrelevant to the current decision. And in this case, it's WG, the first and the last. So it's saying keep the first and the last as is. You can do whatever you want with the others. This decision will stick. And in this case, okay, let's do one more example, and I'll make an observation here. Here's another decision. This was another instance was classified negatively. This is a student whose application looked like this and was not admitted. And the PI explanation is this. That's EG. So again, the last 2 guys, if you fix as negative, you can do whatever you want with the others, and still the decision will stick. Now, I don't know if you realize this, but it's as if this type of explanations in this case was not as interesting or did not add much to the previous one. And there is a reason for this. I'll give you one more example where it's a little bit more interesting. There is an equivalence between the 2 types in some case. There is a class of classifiers where the 2 are basically the same in a sense. And this classifier, the admission one, happens to belong to this class. Well, I'll show you that on the next slide. It's very intuitive. But you can think of these a little bit more robust in the sense that, again, once more, once you fix a subset of the features, you do whatever you want with the others. The other thing to realize is MC explanations, even when you have multiple, they're the same length, right? I'm trying to minimize, let's say, the number of positive features. So I tell you the minimum number. So you had 7 positive features, but you can do with 3. But there are multiple 3s. Not here. Prime implicate explanations, they could be of different length. So I can tell you, oh, here's 3 set of features. If you fix, do whatever you want with the others. But if you include those others, those are 4 of them. And if you fix those, you can do whatever. So they're not always the same length in this case. But now I'll tell you about an interesting type of classifiers where they correspond. So these are called monotone classifiers. So what is a monotone classifier? A positive instance remains positive even if we flip some features from 0 to 1. Right? So I give you an instance and it was classified positively, like this guy. Right? Now, there are 2 negative features here. If you flip these negative features in any subset of them to positive, it will remain positive. Right? So in this case, all of these would remain positive, right? So if you have this property, that's called a monotone classifier. At a positive instance, it remains positive if you flip some features from off to on. And for this class of classifiers, it turns out the two guys are equivalent in the sense that an MC explanation corresponds to a shortest PI explanation. That's why in the previous example, the PI explanations were not as illuminating. You really could do with the MC explanations. Now, the interesting question is, how could I tell whether a classifier is monotone? It turns out this is not easy if I give you the classifier in its probabilistic form. But if you have an OBDD classifier, monotone classifiers can be efficiently recognized. So in a way, once you do the compilation, you can tell, do I have a monotone classifier or not? That's actually efficient to tell. That's pretty interesting. And this comes from literature on the OBDDs, all symbolic reasoning. Okay, let me give you a couple more examples, and then I'll end with how do you compute these. I'll show you how to compute the minimum cardinality. That's easy, and we'll leave it at that. This was a classifier that was learned from a data set out there about classifying congressmen into Republicans or Democrats depending on their voting record. So there are 16 bills, and whether they voted yes or no. And then one is a Republican and 0 is a Democrat, and this was one particular Republican. This was their voting record, so this is the instance. The classifier classified them correctly as a Republican, and then you say why, or, there are those guys that were yes votes. And then the MC explanation says, even though there are, I think, 7 of these 3 alone would have done it. This guy voted positively on these 2 and that, he would still be classified as a Republican. And these happen to be this. And there are further, this is not a monotone classifier. There are further examples on PI explanations, 2 PI explanations, but I will skip that. I want to go to the last part just to give you a hint of how easy it is to compute these minimum cardinality explanations. Now that you have an OBDD, computing prime implicate explanations is a little bit more involved, so we're going to skip it. The key observation that I want to make is these OBDDs that you've seen are circuits in disguise, and you are more familiar with them than you think. If you look at a node like this in an OBDD, which says if X is true, go this way, if X is false, go that way, you can think of it as a little circuit structure that looks like that. This is an OR gate and 2 AND gates, and this is saying X and alpha, or not X and beta. This is basically the same logic as that. And if you do it this way, an OBDD like this is adjusting for notation ends up being a Boolean circuit like that. And the correspondence is in the sense that if you give me an instance of the variables and this guy will map them to 1, then this guy will evaluate to true under the same variable instantiation. While if this guy maps it to 0, this guy will evaluate to false. So this is a Boolean circuit that is mapping instances of x1, x2, x3 to either true or false depending on whether they are classified positively or negatively. And the reason I show you this because this business of computing minimum cardinality explanations is a special case of a more general computation called minimum cardinality that is known to be efficient on circuits if they're decomposable. You've seen decomposable circuits before. Those are the DNNF circuits earlier on. And we knew from a while back, a couple of decades, that you could do minimum cardinality computations on these guys pretty efficiently. And computing the MC explanations was done based on that. So I'm going to just show you the procedure very quickly next. Basically, it's linear time on these guys. So the other observation is if you take the OBDD and translate it into a circuit like this, it will be not only decomposable, it will also be deterministic. So these guys are decomposable circuits, and therefore they have the right properties to do minimum cardinality computations easily. What I'm going to explain to you now is the general result that we knew from a while back in AI. And actually it was used in the context of doing diagnosis. that is immediately obtainable here. So if you have a theory like this, a propositional sentence, and you look at its models, right? The variable instantiations that will make it true. Then you can talk about the cardinality of one of these models, which is, in this case, we're going to count how many variables are true. So if you look at the first guy, 4 of them are true, correct? Second guy, how many are true? 2 of them. And so on. And then what my goal is to find the minimum cardinality among all of these models. So in this case, let's say it's 2. So the question is, if I give you this set of or propositional knowledge base, can you easily compute the minimum cardinality? That's the question. And the second question is, can you find the minimum cardinality models efficiently? It turns out that if you can do that, then you can do the minimum cardinality explanations. And those questions can be answered easily if your knowledge base is available as a DNNF or as a circuit, tractable circuit that you've seen. So let's just run through this quickly. By the way, you could do cardinality by counting how many positive variables, or you can do the other way around, which is counting how many negative variables. So in this case, only 1 negative, and in this case, 3. It really doesn't matter. In the examples we're going to do next, we're going to count negative ones. So we'll define cardinality as the number of variables of variables. But again, they're symmetric. Okay, folks, very quickly, because we're running out of time. Here's a circuit that represents a Boolean function, and I want to compute the minimum cardinality. That is, I'm going to, among all its models, if you look at the cardinality of each and find the minimum, which is that. It's very easy. You start at the leaves, negative literals get 1, positive literals get 0, and you move up, minimizing at all nodes and adding up at AND nodes. The justification is relatively simple. We do this, by the way, usually in the course that I was supposed to teach in the spring. We learn about all of this. So minimizing, adding, number 1. What does that mean? That means if you look at this circuit and look for every input that allow it to evaluate to 1, the models, the positive instances, and you compute the cardinality of each one, and you take the minimum against those, it's going to be 1. In one pass. Done. Right? Now you can do even more. So here's another example. So I did the minimum cardinality. I also get a 1 in this case. Look what I'm going to do now. I'm not only interested in knowing the number 1. I want you to enumerate all possible minimum cardinality models. So this circuit can be satisfied or evaluates to 1 under a number of instantiations of A, B, C, D. Some of them have minimum cardinality, which happens to be 1. And some of them have higher cardinality. I want those guys that have the highest cardinality. What do you do? It turns out to be also easy. In this case, it's not enough to be decomposable. You want it to be smooth. Again, we discussed this before. All you have to do is you go to OR nodes, and if an OR node has a child that has a higher cardinality, like in this case, 0 and 2, you kill the 2 guy. You remove it. That's all you do. OR nodes and kill the children that have not the lowest cardinality. So in this case, only this guy will lose a child and only that guy will lose a child. This guy, both of them are 1, stay, and so on. So you kill these 2 guys. Look what happens. You prune this circuit. You remove these 2 edges. Now these guys are dangling. This and that. You remove them. And now what do you have? A smaller circuit. Guess what? Guaranteed. The models of this new decomposable and smooth DNNF are precisely the minimum cardinality models of the previous guy. I just handed you the minimum cardinality models. So if you're doing explanations, I just handed you the minimum cardinality explanations in a tractable circuit. So you can easily enumerate by going from the top. And for an OR node, you choose one of the children. For an AND, you choose both. So this is what happened here. Only 1. And you can see that this subcircuit, which you're familiar with this notion of a subcircuit, we did it for ACs when we had adders and multipliers. If you look at this subcircuit, it's this instantiation. Now let's say we choose this child instead, or we choose that, then you enumerate the others. In this case, we enumerated this guy. Now we enumerated that. Now this. So there are 4 of them. Go back. We did minimum cardinality. We pruned some of the edges, and we enumerated. To use this to do minimum cardinality explanation, you need one extra step. You will see them in the slides. I'm going to skip them and just. Okay. I was given the signal that we were done. So we are done.